Hi, today we're going to go over the Machine Learning Coursera course, Practice Lab Advice for Applying Machine Learning. In this lab, we're going to explore techniques to evaluate and improve our machine learning models. Packages. We're going to import NumPy, Matplotlib, scikit-learn, and TensorFlow. Evaluating a learning algorithm with polynomial regression. So we have created a machine learning model and we find it fits our training data very well. But we are not done because the goal of creating the model was to be able to predict values for new examples. How do we test our model's performance on new data before deploying it? We can split the dataset into training and test sets and develop an error function to evaluate our model to see how well it does. So in this diagram, we see that the model fits very well on the training data, but fails to fit the new data. Splitting our data set. Lecturers advise reserving 20 to 40% of our data set for testing. We're going to use scikit-learn function train test split to perform the split. In this example, we are using a test size of 0.33, which means that 33% of our dataset will be in the test set and 77% will be in the training set. Here are the shapes. Plot train test sets. So we have plotted the training set and the data and the test set, and we want our model, ideally, which is the y ideal, to be able to generalize well to new data. Error calculation for model evaluation, linear regression. So when evaluating a linear regression, we can average the squared error difference of the predicted values and the target values. This is called the MSE. So our job in this function is to evaluate the error on dataset for a linear regression model. And the error will be the mean squared error, or MSE in this example. We have y, which is an array for the target values, and we have y hat, which is an array for the predicted values. And we want to return error, which is a number. So we have m, which is the length of y. We have error, which is 0.0. And we're going to start iterating. So for I in range of m, so we're going through the sigma over here, we're going to do y hat, because we're going to use y hat I because y hat I is FWB at I, minus yi, and then we're going to square that, and then add it to the error, and then in the end we're going to divide by 2m. So that's the plan. We have error at I, which is this term in the parentheses over here. So error I, we're going to set that equal to y hat I minus yi squared. Then we are gonna add it to the error. So error plus equal to error I. And then once we're done, we are gonna divide by 2m. So error is equivalent to error divided by 2 times m. The parentheses are important because 2 times m is at the bottom. And all tests passed. Now we're going to compare the performance on the training and test data. So we are going to build a high degree polynomial model to minimize training error. And the steps are create and fit the model, and then compute the error on the training data, and then compute the error on the test data. And we're going to see that. And notice the degree for our polynomial function is 10. And it's a linear model, lin model. and this dot fit fits it on the X train and Y train. And we were printing out the values, and we noticed that the training error is 58.01, which is way lower than the test error. And we're going to see why over here in this plot. So we noticed that the predicted model is fitting the training data very well, because you see that it hits the training data at every single point, it seems like, but it doesn't even touch most of the test data, and that is why the test error was so high. And ideally we want this dotted line, this dotted orange line, to be able to kind of get some of the training data wrong and get error on the training data, but also be able to generalize well to new data. And so this model would be described as 1. Overfitting, 2. High variance, 3. Generalizes poorly. And so because of this problem, we need another set of data to test new data performance in order to run different models. And the proposal in lecture was to split the data into 3 different groups. And we're going to go over that. In this little graph, it says that for our training data, 60% of it should be here, and it will be used to tune or change model parameters W and B in training or fitting. And 20% will be in cross-validation, and it will be used to tune or change other model parameters like degree of polynomial, regularization, or architecture of a neural network. And 20% will be in test data, and it will be used to test the model after tuning to gauge or see performance on new data. And we're going to do that over here with this code. And now we have training and test and cross-validation data sets. Bias and variance. It was clear that our degree of our polynomial model was too high, which was 10. Now, how do we choose a good value? Now, it turns out we can look at our graphs for training data and cross-validation data, and we can look at the error function and choose the optimal degree this way. So in this example, this optimal degree is over here, where it has a low cross-validation and cost function and a relatively low cost function for training data. Plotting our training, cross-validation, and test data. And this is our data. And we want our y-ideal line to be able to fit it like so, and not overfit or underfit. Finding the optimal degree. We are gonna try 9 different degrees of polynomials and plot the result. And we see 9 different graphs, and we notice that the optimal degree lies at degree 2, where it has the lowest cross-validation error and a relatively low training error. And the y-ideal line is this dotted orange line, and y equal 2 is this thin orange line, which is kind of hard to see, but if you notice very closely, it's very close to this y-ideal line. And this is explaining how this plot demonstrates and determines if the model is underfitting or overfitting. Now we're going to tune regularization. So our regularization parameter lambda are these values in this array going from 0.0 to 1 times 10 to the negative 6 all the way until 10 and 100. Now we're trying different regularization parameters, and we notice that our optimal lambda sits at this value, which is, I believe, 1. And this is the predictions versus data graph. Now we can get more data or increase the training set size M when our model is overfitting, and this can be used to improve performance. But we note that adding more examples when it has an underfitting problem does not improve performance. And we notice that as we increase the number of examples M, we can generalize very well to new data. Evaluating a learning algorithm for a neural network. So we're done tuning a polynomial regression model. Now we'll work with a neural network model, and we're going to start by creating a classification data set. So we're going to run this cell, and it's going to split our data for training data, cross-validation, and test sets. And note that we are increasing the percentage of cross-validation data. Now this is going to graph our data out. And we notice that there are 6 different blobs, and they are separated very well into different clusters. Evaluating categorical model by calculating classification error. The evaluation function for categorical models is simply the fraction of incorrect predictions. So 1 over m times sigma 0 to m minus 1. And it'll be a 1 if y hat is not equal to y, and otherwise it'll be a 0. Note that it is not one-hot encoded. So we have y, which is an array for target values, and y hat, which is an array for predicted values, and SIR, or classification error, is a number which we are returning. So we have m, which is the number length of y, which is the number of training examples, or number of examples, and incorrect is 0. And for I in range of m, we are simply going to run this if statement. If y hat I is not equal to yi, then the number of incorrect examples will be increased by 1, and 0 otherwise would do nothing. And then in the end, we are going to take our classification error, SIR, and set to be equivalent to incorrect divided by m, so divided by m. We're going to run it, and all tests pass, and we can see the categorization error. Model complexity. We're going to build 2 different models, a complex model and a simple model. So we'll evaluate the models to see if they are overfitting or underfitting. So first, this is the complex model, and I already have the solution over here because it's quite long to type. So we have a 3-layer model. So this is the model, and the dense layer will have 120 units with a ReLU activation, another layer with 40 units, ReLU activation again, and 6 units and a linear activation. So linear activation and classes of variable we have from above, which has a number 6 in it, and we're going to name it complex. And then we're going to compile it using a sparse categorical cross entropy function with from logis equal to true, and an atom optimizer with a learning rate of 0.01. And we're going to start fitting the data on X train, Y train, and 1000 epochs. And it's running a while, but we notice that the loss function is going down from 1.1 all the way to 0.2, and then so on and so on. And this is a summary of our model. And this is making a model for plotting routines to call later on and graphing it. So we notice that it's roughly fitting these blobs of data. And let's see the classification error. And we see that it has miscategorized some data, and this is in percentage. So for example, on the categorization error for the cross-validation, there are 12.2% of our data which is misclassified. Simple model. Now let's try a simple model. This will only have 2 layers in it, with a dense layer with 6 units and activation ReLU, and dense layer with 6 units and a linear activation, and the same loss function and atom optimizer. And this time we're going to name it simple. And we're going to see the summary. And notice how it's a lot faster than the complex model. Now we're going to graph it and see the classification error. And we compare with the complex model, and note that our simple model has a clear classification error on training data, but it has a better cross-validation error than the complex model. Regularization. We're going to apply regularization to see the impact on the complex model. Now first, in our model, we're going to have a dense layer with 120 units, ReLU activation, and this kernel regularizer with a value of 0.1, and we're going to do the same thing but with 40 units below, and then use a dense layer with 6 units and a linear activation and call it complex regularized. Then we're going to compile it with this loss function and this atom optimizer. Then we're going to run it and fit our model and see the summary of our model. And it's taking a while, but now it's done. So this is going to graph it. And check the classification error. And we note that the simple model is better than the training set, but than the regularized model, but worse in the cross-validation set. And here are the numbers. Now we are going to iterate to find the optimal regularization value. So we can try many different regularization values, and this code takes several minutes, so I'll edit the video over here. Okay, so it's done running. Now this is a graph of tuning the regularization, and we note that as we increase the regularization, or lambda, as we increase lambda, the performance of the model on the training and cross-validation data sets converge. They meet at this imaginary line in the middle. And for this dataset and model, lambda, which is greater than 0.01, seems to be a reasonable choice. Now we graph our simple model, regularized model, and ideal model, and we see that the simple and regularized model seems to be very, very close to the ideal model. And we are done.